Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with yet another geometry video for you all. And this lesson topic that we're going to be going over now is tangents and circles. Now, this is basically a bridging into our new unit, which is all about conic sections and circles. I've combined two larger units, and I've finished that off with our 3D shapes. And now we're going to be combining two smaller units into one giant unit called circles and conic sections. We're going to be starting this off with our circles part, and that's going to be introducing tangents and circles. Now, I've already introduced the basis of circles to you guys with area and perimeter formulas and similar properties of circles as you might come across, their different parts, and etc. But now we're going to be looking at different relationships with different figures correlating with your circles and some identifications that we got to in order to develop, say, for example, your area formula, your perimeter formula, your circumference formula, and so on and so forth. But before I jump into this lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as turning on post notifications by hitting that little bell icon so you don't miss out on any of our channel's latest uploads. So the whole theme and purpose of our lesson today is to discover what are the different types of tangents and what are the relationships with circles. So we're going to be identifying the different kinds of tangents, what they are, and their correlations with circles. So without further ado, let's jump right into it. Let's start off by looking at tangents of circles, their basic breakdown, what they are in their organic form, and then later on throughout this video, I'll be showing you the different branches of tangents. But for now, tangents of circles part 1, let's just look and focus hypertensively all about tangents. So a tangent is a line on the plane of a circle that intersects the circle in exactly one point. Although that definition is pretty straightforward, let me still explain. A line is on a plane is basically saying that any line that is located on a two-dimensional outlook that is of the same of a circle. We know that a circle is a 2D figure, and we know that a plane is a two-dimensional outlook on a 3D overview. So a line that's located on the same plane of a two-dimensional circle, as the circle states, that intersects the circle in exactly one point. And the point of tangency is the point where a circle and a tangent meet. So that's the intersection of a tangent and a circle. And that point actually describes and further represents all of the relationships between the said circle and the given tangent. So this is an example here. As you can see, our screen here would actually be our two-dimensional outlook. It's going to be a two-dimensional outlook on any possible 3D outlook. If you're looking at this on a device, that would be your 3D overview. But this is our 2D plane that we're looking at now. And we're going to be referring to the circle and the tangent that are located on the same exact plane. So if you look here, I've labeled this here as tangent. This is our tangent here intersecting the circle at one constant point. And that one constant point would actually describe all of the relationships between this tangent and the circle, and also proving that they're on the same plane. So I'll write this here. This is our circle. And this is our point of tangency of our tangent. So I'm just going to underline all these. And as I said, this point here, point of intersection, point of intersection, equals your point of tangency. Now, you might know what tangent means from, your grammar lessons from maybe your English classes. A lot of them revolve around tangents or tangible, or it's mostly looked at as an adjective in English. So what tangent actually means is that something that's able to be described through sensory feelings. Now, you might think, what does that have to do with this? It's when you use your senses to actually describe something or, correlate with something. Now, if you look at this example here, we have this tangent and it intersects the circle here. Now, since they have some sort of contact, you are using a sensory adjective, which is touch. And that touching point, that point of tangency, is what's going to describe all of the relationships. So I just want to label out some items of tangency, some properties of tangent. So I'm going to write tangent up here. Tangent, it'll always be on the outside, so exterior of the circle. And that is because if any line, a line is always going to increase. So I'll say infinite length. I'll label these out and I'll explain them afterwards. So it's going to be exterior to a circle. It's going to have infinite length and 1 point of contact. Now, the reason that I'm writing all of this down is because I want you to utilize this information, and I want you to defer from the later other types of lines and line segments that I'm going to be referring to in this video later on. But a tangent, summarizing its basic properties and its differential properties, is that a tangent is always going to be exterior to its circle. It's going to be described by its circle. So a tangent is always going to be exterior because remember, it's a line. So it's going to extend on for an infinite amount of length, like I said here. And when it extends for an infinite amount of length, if it's on the interior of the circle, that means it must intersect at 2 different points, which is something else that's called a secant, not a tangent. So that means a tangent must always be on the exterior and maintains 1 point of contact, and it's a line, so it's going to have an infinite amount of length. All right, let's move on to tangents of circles part 2, and let's look at secants. Like I was saying, it's 2 points of contact now this time, so we're going to try and defer from tangents and secants, and then later on chords. So a secant is a line that intersects a circle at 2 different points. Keep in mind that tangents and secants have one factor in common. They're both located on that same 2D outlook, that same plane of a circle, and they are both lines. So that means they both have the similar properties of infinite length, and they don't have definite length, unlike our chords, which I'll be getting into in our next slide. And it's a line that intersects a circle at 2 different points. So that's our main differentiating factor here. But it also comes with other characteristics that also differ from a tangent. So secants contain chords. I will show you what that is later on, but it's a type of line segment correlated with circles. But secants contain chords, but do not have their own endpoints because of the fact that they are lines. I want to underline that and emphasize my point here. And it's going to intersect at 2 points. So let's take a look at this diagram here. I have the 3 values, or the 3 types of lines that we're going to be looking at today. We have our secant here, which I am referring to in this slide here, secant. And then we have our tangent line here and our chord here. If you can look here, our tangent line is, of course, a line segment, a line extending for an infinite amount of length, and it's going to have 1 point of contact. And then you have your secant here, which is also going to be a line, not a line segment. And it's going to be on the interior of your circle, and it's always going to intersect at 2 points on the circle, because a line that's located on the interior of a circle is always going to intersect it at 2 points. Any line that's exterior only has a possibility of intersecting once, and that, of course, is your tangent and your secants. And finally, we have our chords here, which I will explain later on, but this is our line segment here, making contact and having endpoints on 2 points located on the circle, and it's, of course, your line segment differentiating itself from a secant. So let's write down the properties of a secant, because that's the slide focus right now. So secant right here. The properties of secants, it's a line, so infinite length because it's a line. Infinite length. So that means we cannot determine its length because of the fact that it's a line, but we can determine different relationships with chords and tangents, and identify central angles or secant angles, so on and so forth. And then, of course, we have the fact that it intersects at 2 points. 2 points of intersection. And finally, last property, a secant will be a line, but it's also going to be on the interior. It's going to be an interior line of the circle because it intersects at 2 different points. So interior to circle. Sorry, interior of circle. I apologize. All right, so those are our properties of secants. Now let's move on to tangents of circles part 3, and now let's look at chords. Now I did make a follow-up video to this video. There's a predecessor, but I did try and incorporate it in that same way. So this is a predecessor to the next video called Chords and Arcs. I will be implementing some of their facts here, but you need to know what tangents, secants, and chords are before you actually watch Chords and Arcs video, because that's going to be more about the theorems of chords and arcs. So I will be going over their basic terms here, but the later theorems or the more complex theorems will be in my next video. And I'll also make a follow-up to tangents and circles, and I'll just be calling them tangent theorems so that you can see the different types of theorems in a higher complexity. But for today, I'll be describing the different properties of chords, tangents, and secants, your basic lines, and then I'll correlate them with theorems that go along with them, the basic building block fundamental theorems. So let's take a look at chords. A chord is a line segment that has endpoints on the circle. Something that I want to point out in this definition is line segment and endpoints. We always know that a line segment has a definite length. So if it has a definite length, we know its exact location, and a line segment is always going to be identified by both of its endpoints. So that means those endpoints are actually going to be located on the circle. And of course, it's going to be on the same exact 2D plane. And of course, you can have chords and tangents and secants that all intersect. So a special type of chord is known as the diameter of a circle, which I'm sure all of you are familiar with coming into this video. A diameter of a circle is basically a line that extends and touches 2 points of a circle. It's a line segment that touches 2 points on the circle and also intersects the center. And it's under a tangent classification, meaning that a chord is under tangent classification in this video, meaning I'll be including tangents, I'll be including chords underneath the classification of tangents, but they are separate artifacts. But in theorems, they'll be referred to and also inferred as part of tangents when referring to the theorems. And the cool thing is, not only is a chord your diameter, because a diameter can be a chord, but not all chords are diameters. That's because a chord can be of any amount of length given on a relative circle, but a diameter has to be consistent length, but not a consistent location. Now, the largest possible chord is actually your diameter. So we're going to take a look here. This is an example of a chord. It does not intersect, but it ends at 2 points on the circle. So it has 2 points to endpoints on the circle as shown here. It has a definite length. So yes, we can utilize that in our later theorems that I will go along next time. And it's under a tangent classification, like I said. And the largest possible, so I'll write this here, largest possible chord is your diameter. That's because it goes through the center of the circle, meaning that it will have the greatest possible distance from the exterior sides. The exterior, the sides of your given circle. Although it doesn't have sides, the arcs of your circle. So that's the largest possible chord. And some properties of chords that I want to write down here, because it's very similar to your secant, so I want to differentiate it from the secant. So it's on the interior, so I'll say interior of circle. It also has a definite length because it's a line segment, so it's definite length. And it has 2 points. 2 points of contact and not intersection. Intersection means you're going through something. However, this has points that are on the circle, so 2 points of contact on the circle. They don't extend outwards outside of the circle, so every part of it is going to be on the interior, always. It's always going to be on the interior. So now let's move on to tangent and secant theorems part 1. Let's utilize what we've actually gone through first, these definitions, and we'll actually put them into our theorems now. We'll utilize them with numeric values. So let's look at the secant chord theorem. So secant chord or secant angle measure theorem states that when you're given two chords or a secant and a chord that intersect on the interior of a circle, the value of the given angle that you're actually describing is going to be equivalent to 1/2 of your intercepted arc. An arc is basically any part of your circle here. So say, for example, we have this entire circle here. I'll just draw this out for you. Say, for example, we have this circle here, given here. We have this given circle here. And say, for example, we have a line that intersects here and here. This little piece here that's being intersected by both of these lines, this is your arc. It's just a part of your circle. It's a part of your circumference of your circle. That's all an arc is. So you're going to be utilizing an arc is defined by a degree measure, same thing as an angle. So you could describe it by the same angle measure. It's going to have a degree measure. And the measure of a central angle is equal to the intercepted arc, but a secant angle is worth half. So what a central angle is basically, if you look at the center here, this is the center of your circle. If you look at the center here, it's any angle or any line that intersects at your center and forms a different angle. So your central angle is going to start at 360 degrees. And as soon as you have two lines that intersect that central angle, you'll have different angle measurements here. And when you're given an angle measurement here, such as this, this pi piece that we've just cut out here, and we're focusing on this angle measure right here, it's going to be worth the same value of this arc measure right here. It's going to be worth the same value of this arc measure right here. However, when you're looking at a secant angle, such as this one, right here with E here, I'll erase this to clear up some space. So if we're looking at this central angle right here, the secant angle right here, it's actually going to be worth half of this arc that it's actually intersecting with both of its lines. So I'll just highlight this here. Yep. So it's going to intersect. So let's utilize this, and let's utilize some numeric values to actually prove this. Now, the reason that I put secant chord theorem, because you might think, oh, it's just two chords here. Well, you can also have a secant here. Say, for example, this line extends outwards. This would be another secant here. Or it could be two secants that intersect that go on for an infinite amount of length. Infinite length. But in this case, we're only referring to chords, which is just your basic value, so I can show you what's going on the interior of your given circle. Clear this up. And now we're going to be looking at this angle measure right here. We're trying to figure out what the value of this angle is in degrees. So let's take our values here. Let's assume that this arc here, this arc CA here, is actually going to be worth 78 degrees. Now we want to discover what the value of the secant angle is, E, this E secant angle here. Now we're going to utilize our equation in order to do so. Now this is a chord, so you could consider it as the chord angle measure, but it can also be considered chord or secant angle measure depending on the problem. So we're going to try and discover what this angle measure is here. So we're going to use our equation, 1/2 times the intercepted arc. Our intercepted arc measure is 78 degrees. So what we're going to do is input this value here. So 1/2 times 78 degrees. 1/2 times 78 degrees equals 39 degrees. So that means the measure of the central angle is this chord or secant angle is 39 degrees. Let's move on to the next tangent and secant theorem, part 2. This is the chord theorem. So this is more of a property that you can use later on that I will refer to with more about chords in our arcs and chords video, but I will also show you this property. And it states that if the radius of a circle intersects a chord, then it bisects it as well. And we can utilize this info to find definite lengths, since chords are line segments, so we can utilize our lengths and to calculate the lengths of, say, for example, your radius and or your line segment. But I will get into depth on how to actually do that with our numeric and formulated values in our next video about arcs and chords. But what that basically looks like here is, if you look at this circle here, we have OC, line OC, and that's our radius here. We have line AB here, and that's going to be one of the chords of this given circle, circle O. As you can see here, it actually intersects at a 90-degree angle in this case. But just keep in mind that a radius has infinite amount of lines, but they always have the constant amount of length. So this location can always change. Now you're always going to have a radius that's going to be perpendicular to any chord that's given. But in this case, since this is intersecting at a 90-degree angle right here, perpendicular, it's actually going to bisect this AB, this chord here as well. So if you know the value of AB, and if OC intersects it, then you know the value of PA and PB as shown here. So all that's saying is it bisects. So bisect, I'll just write this out here. Bisects means that it is perpendicular and it splits into two equivalent parts. All right, now let's move on. Let's look at tangent and secant theorems, part 3. Let's look at this secant and tangent theorem. The secant, tangent, and tangent theorem all revolve around the same relationship called the same relationship of an equation, stating that 1/2 times your intercepted big arc minus your intercepted small arc. And this is representative of all the possible relationships between two secants, two tangents, and a secant and a tangent. So you can always restructure this formula, to represent relationships between all of these values, but mainly between secants and tangents. As tangents and tangents are always going to be consistent with each other, and secants are always going to be of the same properties since they are lines. But I will get into depth with that later on, these relationships, as we go extensively, getting into different powers of properties and correlating between lengths that aren't actually there. Some things that we have to actually memorize. I'll show you later on with our tangent theorems video. But if you look here, we have a secant and secant here. This, if you know the relationship here with one example, then you'll understand all examples here. But all it's saying is, even if you're given just a tangent intersection, this would still work. But if you have two secants here, as shown, these secants are expected to, extend forever in their own directions. So they extend forever in their own directions. But I'm only focusing on this magnified on part. So if you look here, we have our secants intersect at two different parts, and also they extend outwards for infinite amount on these sides as well. But they intersect two parts of the circle, N and O, and then P and G. Now what we're going to utilize is, what we're going to try and figure out is, we're going to try and figure out this angle right here of this intersection between these two secants. We want to find out what this angle measure is here. Now the way to do that is actually, if we know the values of NP, this arc NP here, we know the degree measure of OQ, that means we can automatically figure out what this M degree measure of this angle M is. So if we know that angle N, or arc NP, is 30 degrees, we know that OG is 90 degrees, or a perfect right angle. What is the value of angle M? Now, if you look at this equation, it says 1/2 times big arc minus small arc. We know that the arc that's going to be outermost, or farthest from our secant angle, is always going to be the largest angle. Because by the time those lines extend, they're actually extending to a larger amount, getting farther and farther away from each other, so the intersection is going to be larger. So that we know that OQ is going to be our big arc, and NP is going to be a small arc, relatively, in this equation here. So we're going to plug those values in. So we have 1/2 times our small arc, which is 30 degrees, and our big arc, which is 90, so it's going to be 90 degrees minus 30 degrees. And that's the same as saying 1/2 times 60. Oh, sorry. It should be plus. I apologize. Just correct that here. So this should be plus small arc. So you're actually just finding the averages between arcs. So that's 1/2 times 90 degrees plus 30 degrees. 1/2 times 120 degrees, which equals 60 degrees. So that's the value of M, 60 degrees, our secant angle of focus. Tangent and secant theorems, part 4, our last theorem. It's going to be about tangent perpendicularity, and it's going off of the definition of what a tangent is and just extending forward. So a circle's tangent line is perpendicular to the radius at the point of tangency. So now we know that a radius has an infinite amount of locations. You can have an infinite amount of radii on your circle, but there's always going to be one radii that's going to be perpendicular, meaning it will touch the point of contact, the point of tangency of a tangent, and intersect it, or make contact with it at a 90-degree angle. And the converse of the tangent theorem, basically saying the reverse property of the tangent definition, what tangent line definition of a circle, that is also true. It states that a line that is perpendicular to a radius of a circle at its endpoints on the circle is tangent to the circle. So all it's saying is, if a line that intersects at one point is tangent at that, or is not perpendicular at that point to a radius, then it must be a tangent of the given circle. So I'll show you this example here. If we have two tangents here, as shown, they intersect at one point here. All that's happening here is they're intersecting this circle, and these two lines, your radii, are both intersecting it. They're both of the same lengths, as shown here, and these tangents are both of the same length. They're both intersecting the circle at a 90-degree angle as shown here. So I'll just highlight that at 90-degree angles here. And when you're doing that, actually, after you develop those lines here, say for example, you want to find the length between your center and a given external point here. You can use your Pythagorean theorem here, because you can actually develop a right triangle here. If you want to find out angle measures here, say for example the central angle here that these two radii develop, you can also utilize that by calculating your angle measures here and here. If you have special triangles such as 30, 60, 90-degree angles. So it's going to be a right triangle here. That's an important property. It's going to develop a right triangle. Right triangle. And you can also use your Pythagorean theorem as well. All right, everyone, that'll be it for today's video. This has been the eCoreAcademy e-learning platform today. Please make sure to like and subscribe down below, and click that bell to get notified on any of our channel's latest uploads so you don't miss out on a single vid. Please visit our website at www.ecoreacademy.org. There we have full unlocked access to what we as an e-learning platform actually offer for you. The full package. We have integrated quizzes, note sheets, and worksheets that go along with each and every single one of our videos, organized into their own lessons under their own specific course studies by subject. We have progress checks, other events, tips and tricks, and some extra packages that you might get as well, and bonuses that you will get if you just sign up for free, make an account for free, and join our website there as well on top of our YouTube video. Also visit our website. Also email us at eCoreAcademy@gmail.com. It's also located on our website as well. And finally, visit all of our socials in the description box below. We have the full links down there. But please visit our social medias at Facebook, Twitter, and Instagram at eCoreAcademy. See what kind of interesting content we have there aside from our website and our YouTube channel, and use our mediums to share all of our videos. Once again, everyone, this has been AJay Raj. I had a pleasure making this video, and I hope you guys enjoyed. And I will see you guys in the next one. Peace.